In this video, we're continuing our discussion of single degree of freedom systems, and we'll be finishing up Chapter 2. Here we're going to talk about equivalent mass and equivalent stiffness. So often, multiple mass or spring elements in a system can be lumped together for the purposes of analysis. If these elements are linked together, they can be thought of as a single equivalent element of stiffness or mass. This equivalent element is called the effective mass or effective stiffness of the system. So let's look back at our equations of motion for simple single degree of freedom systems. So like a simple spring mass system, we had the standard form of the equation of motion was mx double dot plus kx equals 0. And for a simple pendulum, the standard equation of motion is given as shown here. So ml squared theta double dot plus mgl theta is equal to 0, where L is the length of the pendulum and theta is the angle, which is used as the coordinate in that case. Now, both of these systems have a common form that is some m, some sort of mass element, multiplied by the coordinate double dot, so the acceleration, plus some sort of stiffness element multiplied by the coordinate, or the deflection, is equal to 0. So Q is the chosen coordinate for the problem, which can be any coordinate. You can see for the spring mass, linear spring mass systems, it's x, and for like an angular system, like a pendulum, it's theta. And then M effective and K effective are the effective mass and effective stiffness of the system. So M effective is just everything that's in front of that Q double dot, and K effective is everything that's in front of the Q when it's written in this form. And then when we have it like this, the natural frequency is equal to the square root of K effective over M effective. Now we can find the effective mass from Newton's laws or from energy methods. The effective mass can also be found from inspection in certain cases. Now, as an example, the total kinetic energy of a single degree of freedom system can be written as 1/2 m effective q dot squared, where q dot is the velocity. So once we determine the kinetic energy of the single degree of freedom system, the effective mass has already been determined implicitly, because we would already know what this term is. Equivalent stiffness is sort of similar. So equivalent stiffness can be found from inspection when we note that the potential energy of a system, a single degree freedom system, can be written as 1/2 K effective Q squared. Another approach, the other approaches are based on statics and are based on the relationship of the system that F is equal to K effective delta, where delta is some displacement. This is F is the static force applied, and delta is the deflection of the coordinate. Now, there are two main approaches to find this equivalent stiffness or effective stiffness. The first is called a stiffness approach, where we apply a positive unit deflection to the system and find the force F required to maintain this deflection based on statics. So K effective is then equal to F over 1, because this is our unit deflection that we're applying. So really, K effective is just equal to the F that we find. The other approach is kind of the inverse of this. It's called the flexibility approach, where we apply a positive unit load, so either a force or torque, to the system and find the resulting deflection. So in this case, K effective is 1 over the deflection. So these stem from that static relationship that we talked about, where F is equal to K effective delta. So in this case, we're applying a unit load and finding the resulting deflection, and then we can calculate K effective as 1 over that deflection. So we can generalize this to not just linear displacements, but also angular displacements, where we apply the stiffness approach. We apply either a unit deflection or an angular rotation. And then K effective, for linear displacements, K effective is just equal to the F that we find. And for angular displacements, K effective would be equal to the torque that we find. And when it's angular displacements, to kind of distinguish the K, because it would have different units, we put this little hat on it typically. The flexibility approach is, again, the inverse. So we apply a unit force or torque, and then we find the resulting deflection. So for linear displacements, K effective is 1 over that deflection. And for angular displacements, K effective is equal to 1 over that resulting angular deflection. And again, to distinguish the angular stiffness, we put this hat over the K effective. So these are very powerful approaches that allow us to use statics to find an equivalent representation of the system in terms of equivalent mass and equivalent stiffness. And we can see quite a few different examples of this.